Here are the answers for the section 14-4 homework. Question number 1. Two roots of this equation are 1 and the square root of 2 times I. This is a real number root. This one's an imaginary root. The question is, what is the other root? Because if the polynomial goes to the third power, there are going to be 3 roots. One of the theorems from this section was, whenever there is an imaginary root, its conjugate is also a root. So the conjugate of square root of 2i is negative square root of 2i. Now we're asked to verify. We could verify that by direct substitution, where you plug the number in for x and then evaluate it to see if you get 0. Or we can verify with synthetic substitution, where we plug the number in with the synthetic substitution and check to see that the remainder is 0. I'm going to use synthetic substitution. 1 from the x cubed, negative 1 from the x squared, 2 from the x term, and negative 2 is the constant term. And the number that I'm going to substitute in is the negative square root of 2 times I. Now let's run through the process. Bring down the 1. 1 times negative square root of 2i is negative square root of 2i. Now add these together. This is a real number and an imaginary number, so you just write them side by side. Now multiply this by what's out front. Negative 1 times negative square root of 2i is positive square root of 2i. Negative square root of 2i times negative square root of 2i makes positive 2i squared. But that makes negative 2. Now we're going to add these together. The 2 minus 2 will just make a 0. So this is the square root of 2i. Take that and multiply it to what's out front. So square root of 2i times negative square root of 2i makes negative 2i squared. But that just makes 2. And when you add these together, the remainder is 0. So that's our verification that this one is a root of the equation. Next, number 3. A cubic equation has roots 3 and 1 minus 2i. What's the other root? Again, the theorem is that if there is an imaginary root, then its conjugate is also a root. So the conjugate of 1 minus 2i is 1 plus 2i. Now we're asked to find the equation. We know what the roots are, so we can build the equation in its factored form. If 3 is a root, then x take away 3 is a factor. Because if you plugged in 3 where x is, 3 minus 3 would make that be 0. If 1 minus 2i is a root, then x minus 1 minus 2i is a factor. Because if you plugged in 1 minus 2i where the x is, and then subtracted this, that would make a 0. Now the third factor, x minus 1 plus 2i. And that's equal to 0. Here's the equation, but we can simplify it up a little bit in the parentheses. This is x minus 3, and then inside here it's x minus 1 plus 2i. And then in these parentheses, it could be written as x minus 1 minus 2i. And that's equal to 0. So here is the equation in factored form. Next, number 5. One root of this equation is 2 minus 2i. Find the other roots. Well, this goes to the third power, so there are going to be 3 roots. Here's one of them. This is an imaginary root, so its conjugate is also a root. So 2 plus 2i will be one of the roots. Now there is going to be a third one, and it's going to be a real root. There are different ways to discover that real root. One of them is to use synthetic substitution to try to divide in some real numbers to see which one works. That's the technique that I'm going to use. 2, -11, 28, and -24. Now I'm going to try real numbers until I get a remainder of 0. Maybe it's 1. So this is 2, 2, -9, -9, 19, 19, and -5. The answer is not 1. So let's erase and try something else. Maybe it is 2. So 2, 4, -7, -14, 14, and 28, and then 4. The answer is not 2. When I tried the number 1, do you remember what we got in the remainder spot? We got a negative number. And now we've tried the number 2, and we've gotten a positive number in the remainder spot. So the answer has changed signs from negative to positive in between a 1 and a 2. I think the answer maybe is something that's in between 1 and 2. Maybe it's 3/2, because 3/2 is 1.5, and that's in between 1 and 2. Let's try it and see what happens. 2 times 3/2 is 3. This is -8. This makes -12, 16, 24, and 0. So the remainder is 0, so 3/2 is a root. We can add that to our list. So here are the other 2 roots. Next, number 7. One root of this equation is 1 minus 3i. Find the other roots. This goes to the 4th power, so there are going to be 4 roots, and we only know one of them. Because this is an imaginary root, its conjugate is also a root. So 1 plus 3i is going to be one of the answers. But there are 2 more that we need to find. Maybe they're real roots. If they are real roots, we can use the synthetic substitution technique and just try some numbers. Let's write out the coefficients. 1x to the 4th, -3x to the 3rd, 6x squared, 2x, and -60. Maybe 1 is a root. Let's run through the process. Nope, 1's not a root because we didn't get remainder 0. We got a remainder of -54. Now let's erase that and try a different number. But remember when you tried 1 that this number was -54. Let's try 2 and run through the process. Nope, 2's not right either. We got -40. When we tried 1, we got -54, which is really far from 0. When we tried 2, we're at -40. That's still pretty far from 0, but you know what? We're moving in the right direction. We're getting closer to making this be 0. Let's try to divide in a larger number than 2. I'm going to try 3. And 3 is a possible number to try because remember the technique about looking at factors of the constant and dividing by factors of the leading coefficient? 3 is a factor of the 60, so it's worth trying. And we get a remainder of 0. So the real number 3 is one of the roots. Let's add it to our list. We have one more root to find, and it's going to be a real number. Let's continue on with synthetic substitution. what's another number that we should try to divide in? Well, I'm not going to try any more positive numbers because do you notice how these are positive numbers? If I start running through the multiplying and adding process, things are going to just keep increasing as we move across, and there's no way it can turn out to be 0 here at the end. So we need to try a negative number. Maybe it's -1. Nope, that didn't work. And the remainder was 13. Let's try another negative number. Maybe -2. And the remainder is 0. So we discovered that -2 is also a root to the original equation. We can add it to our list. So here are the 3 other roots. Number 9, let's factor this polynomial over the set of real numbers and then factor over the set of complex numbers. This one right here can be factored using grouping, which is a technique that we learned earlier in the year. Group these together and group these together. So this can be written as x squared times x plus 1 plus, and now this one over here, this is just a single x plus 1. So this can be written as 1 times x plus 1. This makes x plus 1 times x squared plus 1. The x squared plus 1 is not a factoring pattern that we can factor in the real numbers. It's not a difference of squares or a trinomial that uses FOIL or any of those things. So this is as far as we were able to factor earlier this year. This takes care of question A, factoring with real numbers. But for question B, if we're allowed to use complex numbers, then we can factor it farther. So we can rewrite it as x plus 1, and then we can factor the sum of squares using a double parenthesis pattern. X times x makes the x squared, and then to make the positive 1, we can go plus I times negative I. Do you agree that x plus I times x minus I makes x squared plus 1? Let's check it out with FOIL. Remember, the x times x is your x squared. Your outer product is x times negative I, but the inner is I times x. Those are opposites and will cancel. When you do the letter L in FOIL, you have I times negative I. That's negative I squared. But remember how I squared is -1? So this makes the negative of -1, which is plus 1. So in that earlier chapter about factoring, whenever we got x squared plus 1, we were done. But now that we know about the symbol I, we can factor a sum of squares. Number 11, we're asked to factor this. I'm going to begin by using synthetic substitution. 1, 0, -8, and 3. Maybe the number 1 will go in there. Let's run through the process. Nope, we did not get a remainder of 0, so 1 doesn't work. Let's erase it and try something different. It's not worth trying 2 because when you run through the possible roots test, 2 is not a factor of the 3. Maybe 3 works. Nope, that didn't work out. Maybe it's a negative number that we need to use. Let's try -1. Nope, still didn't get a remainder of 0. There's only one more number worth trying, and that's -3. Hey, we finally got it on our fourth try. We were asked to factor, so far we've discovered that x minus -3 is a factor. You certainly could write that as x plus 3, and you should. Now, what are the other factors going to be? We need to keep going on this. We have depressed our polynomial enough that we can now change it back to polynomial notation. This is 1x squared minus 3x plus 1. Earlier this year, we were not able to factor this because there were no two numbers that multiplied up to 1 and added up to -3. So over the set of real numbers, the best we can do is get our x minus -3 times the x squared minus 3x plus 1. That's part A. Now for part B, we want to think about, would we be able to factor this if we used imaginary numbers? I think even if we try to use the letter I, we're not going to be able to get +1 in this position and a -3 in this position. So over the set of complex numbers, it factors in exactly the same way. Now on this question, I don't want you to think that there's no way to rewrite this trinomial as a binomial times a binomial, because there is. There is another theorem that we haven't studied yet about polynomials, the linear factorization theorem, that says that you can factor a third-degree polynomial using 3 linear binomial factors. So right now we have one binomial factor, but the other one's a trinomial. So there does have to be a way to factor this trinomial. And there is. Do you remember earlier this year when we were studying completing the square? So you have the x squared minus 3x, leave a little space, and just move the +1 over to the side. Then we would take half of this number, which is -3/2, and square it, which is 9/4, and add it into this blank spot. And then to compensate for adding 9/4 in there, minus 9/4 right here. This right here creates a perfect square trinomial, and it can be written as x minus 3/2 squared. And then over here, the 1 minus 9/4 can be written as -5/4. Now we have a difference of squares, and a difference of squares factors with a double parenthesis pattern. X minus 3/2 plus the square root of 5/2, and x minus 3/2 minus the square root of 5/2. This can be simplified as x plus the square root of 5 minus 3 all over 2, and then over here it could be written as x plus negative square root of 5 minus 3 all over 2. The point is, if we wanted to factor this cubic polynomial using all linear binomial factors, then this trinomial piece could be written like this. Number 13, we're asked to factor completely over the set of real numbers. This one can be factored using the grouping technique as x cubed times x plus 3, and then minus 8 times x plus 3. So in turn, that is x plus 3 times x cubed minus 8. But the x cubed minus 8 is a difference of cubes, and we had a way to factor that. So we have our x plus 3, and now following the pattern for factoring a difference of cubes, it makes a small set of parentheses and then a little bit longer set of parentheses. It's x minus 2, and then x squared plus 2x plus 4. the x squared plus 2x plus 4 is not going to easily factor using FOIL. However, if we wanted to get that written using two linear binomials, we could run through the completing the square process like shown right up above. So this is as far as you probably would go when factoring over the set of real numbers. If you're allowed to factor over the imaginary numbers, would that get you anything different? To know that, we're going to have to factor this trinomial. So here's our answer for part A. Now for part B, it's going to be the x plus 3 times the x minus 2. And then let's see if this can make anything when we work on it. Let's take the x squared plus 2x and move the 4 over to the side, creating a blank spot. Half of 2 is 1, 1 squared is 1, so put a plus 1 here, but then a minus 1 here. Then this becomes a perfect square trinomial and factors as x plus 1 squared. This piece right here makes plus 3. This is now a sum of squares, which we can factor using the symbol I. So a sum of squares factors with a double parenthesis pattern. We have x plus 1 plus the square root of 3 times I, and then we have x plus 1 minus the square root of 3 times I. So for part B, the original polynomial factors as x plus 3 times x minus 2 times x plus 1 plus the square root of 3i times x plus 1 minus the square root of 3i. Now for the review. Solve this equation. Let's use the synthetic substitution technique to get started. 1, negative 6, 11, negative 6. And I'm going to try dividing in 1. 1, 1, negative 5, 6, 6, and 0. That worked. And it depressed the equation. We can rewrite it as x squared minus 5x plus 6 and set that equal to 0. Now let's try to solve this. It factors. And the first answer we get is x equals 3. And for this one here, x equals 2. So our solutions are 1, 3, and 2. Number 6, find the zeros. That's actually a lot like what we were just doing. Let's use synthetic substitution. 1, negative 3, negative 10, 24. And I'm going to try 1, see what happens. Nope, it didn't work out. We did not get a remainder of 0. Let's erase this and try something different. Maybe 2 will work. Yep, we got a remainder of 0. So one of the zeros is the number 2. And we have now depressed our polynomial. We can write x squared minus 1x minus 12 and set that equal to 0. Now solve it. This one factors x minus 4 times x plus 3. So in the first parentheses, we get x equals 4, and here we get x equals negative 3. So our zeros are 2, 4, and negative 3. Now number 10, given that one of the roots is negative I, find the other roots to this equation. Well, one thing I want you to notice is this equation is not in standard form. It doesn't say equals 0. So we need to put it in standard form. The 2i can be subtracted to the left side. So there's something you really got to watch out for. Is your polynomial equation in standard form before you start doing any work with it? Now, if one of the roots is negative I, then one of the theorems said its conjugate is a root. So positive I is going to be one of the roots. Now, there's going to be one more root, because if it goes to the third power, there are in total 3 roots. Negative I and positive I are both imaginary, so the other one must be a real root. We could find it using the synthetic substitution. 1, negative 2i, 1, negative 2i. Let's try 1. Nope, this last spot did not turn out to be 0, so using 1 doesn't work. Let's try something else. Maybe it's 2i. Let's run through the process. And the remainder is 0. So that other one is 2i.